The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everyone, I am geologist Philip Ong, here with Mr. Dane DuPont of HawaiiTracker.com, bringing you guys another Kilauea and Mauna Loa volcano update. Today, Thursday, July 8th, 2021. It's pretty quiet on both volcanoes, so we're going to take a little time today to go into a couple of different tangents, one being a couple of earthquakes happening north of the islands in the past week, 4.2, a couple of them, and a 5.2. And we'll talk about whether they relate to possible tectonic flexure, the settling earthquakes, or whether there might be some less known, more obscure connection to the Molokai fracture zone, and some bigger earthquakes have happened there in the past, including a 7.5 on Lanai and a 6.8 on Maui in the past. But then we'll jump to Mauna Loa. We'll cover Mauna Loa. Mauna Loa is pretty quiet, still similar patterns as the past few weeks. And we'll talk about the 1975 eruption of Mauna Loa, as that is the topic of this week's USGS Volcano Watch. And that is our outline today. But we're going to start with Kilauea, as usual. We are going to stop in the middle and take questions on both volcanoes. Dan will try to answer what he can in the chat. He'll monitor our streams. So if there's anything with our streams that you can report back to us, if the sound's not coming through or the quality is off or something, then please just let us know and we'll do what we can to fix that mid-course here. All right, so we'll start off with Kilauea, and this is an image from the B1 camera looking west into Halemaumau crater within the summit of the volcano. And no change there really, it's just a different view to refresh ourselves of what it looks like in there, and not a whole lot of changes happening in there, in fact. So yeah, there's not a whole lot of of new imagery to really share with you guys, but we're gonna share the context that we can as it's necessary, and we'll try to keep it efficient for you guys here. So we'll move on to what's the most important difference here recently. That's the earthquakes, right? So here's our earthquake pattern over the last week. And what you can see is we do still have earthquakes under the summit region, right under here. And we have resumed once again Upper East Rift Connector. That's the segment right in here, earthquakes. You can see that there's definitely some magma movement causing very interesting quasi-linear, a little bit snake-like feature here that's likely related to the path of magma through there, which is really interesting that it comes up this sharply. With a little bit of a cluster here at the end, a tail end where Imaginary Pressure is building the most. That is down here near the bend, right by Mauna Ulu. Mauna Ulu is right in here. And so we'll see how that develops in the future, right? Interesting because we have talked about this in the past week where we saw patterns in this Upper East Rift Connector in the past, about a month ago, and under the summit been more steady, but off and on depending on exactly which week you bucket here. As far as the East Rift itself, this segment that's more through here, there's a few earthquakes, but really not a whole lot. It seems a little bit quieter in the past weeks right through there. And the south flank is active still. You see you still cluster immediately south of this Upper East Rift Connector right in here, and a few events through here, but it seems also possibly a little less active, maybe not so convincing with this image right here. So south flank still moving, similar pattern, and a little bit of oscillation perhaps with this Upper East Rift segment coming into play here, and more steady beneath the summit off and on here. So that's the earthquake patterns in the past week, and that's really the important thing, is showing that magma is still moving underground in the area. And we can look at the statistics for the counts here, and earthquakes per day is our measure here on the left, going from 0 to 140, and this is a past month here. So you can see that in the past week, we did have a little bit of a higher flurry on the 5th, and then coming back down. But overall, our levels are pretty low compared to this elevated period we had about a month ago, with those summit earthquakes being really the highest counts, over 100 earthquakes per day, back around the 23rd to 24th of June here. And we do see here an extra peak on this plot here. There was also a 4.5 in Dipahala back in this period, back in the 17th, and lots of aftershocks that came along with that. So we can kind of ignore this one. This is not exactly Kilauea, but we did have elevated background through here. And it seems like maybe, if anything, dropped off, but with a little bit of this oscillation, perhaps, is the pattern here for the past month. If we zoom out, all of that fits into the past year here. And so that was just this little segment right in here. And you can see that during eruption, we had a much lower background value. And before the eruption, much higher with a couple peaks. Namely this one right here, that was the precursor to the actual effusion of lava in late December. So we're back to elevated background once again, with the oscillation, those kind of patterns there. Maybe coming a little low here at the right end, and the graph has just pointed out. But just to remind you guys, you got to ignore this most recent bar over here, because that's only half a data set, just like the very beginning of it. We'll also look a little off because of the half a data set right in there. So ignore those in the ends. This one right here is a full data set. That one certainly is a little bit lower than the previous 2 weeks here, but still within that elevated background, higher than we saw before, previous levels during eruption there. So magma is still moving. It's building up beneath the volcano. Exactly where is the tricky thing here, because we have seen reports from USGS in this past week saying that the center of inflation is perhaps shifting to the southern part of the caldera, and we'll talk about that here shortly. But just to recap, here's some of the more obvious observations. No glow anymore at the top. You maybe occasionally see a spot here or there, but we haven't seen that reported in a little while now. So it's still pretty dark in there. In the thermal camera, we can still see that there are these thermally hotter spots in the other areas, right? This around the west vent and this area of the most recent, the last activity of the lava lake within that pit there. And we scan to the right here to look at the scale. We might be getting near 200 Celsius. That's nowhere near actual red lava. So it's still just a cooling effect and shifting of the plates and all of that in there, which we can look at a little more here as well. But first, to make sure we show you guys the gas, let's see if I can get this on the screen a little better here. So our scale is tons per day here. And we are at above 100 down to 60. And our most recent measurements were in this range of 50 to 70. That's us most recent to here from a couple weeks ago. A little bit of a data gap. But then most recently here, at the beginning of the month, we had 110 tons per day before coming back down here to around the 70 range. So we had one higher peak of gas. Perhaps that might be related to something with magma movement, but it's also within that background range, even if it is a little higher. And this most recent point coming back down maybe is giving us, maybe adds a little doubt that this earlier point is really something we can draw much conclusion from here. See if I can get it on the screen here a little better. All right. So get it all on there at one go here for you guys. So that's the gas. As far as the deformation, looking at the GPS of the summit, let's get this a little bigger. You can see that we still have what looks like a inflating, a rising trend here. If I zoom it way in, we can see that we had a more quick increase in the distance across the caldera. That's what this GPS plot is showing us here, before essentially flatlining there and not changing a whole lot. And you can see that this most recent week, there's a lot of spread in the data there. There are some points a little bit higher now, so maybe the average of this entire cluster in there, maybe somewhere in here, you know, it's but they're showing a little more range, and possibly this is actually starting to come up again. We'll see. We've warned about how these data points on the right end of the graph can get refined and move a little bit and be more clear as time goes on. So we'll look back in another week and see what the trend is, but there's a possible hint of it increasing here. And otherwise, it's definitely slowed quite a bit from what it was before, no matter which way you cut it, because it was pretty fast coming through here. Right, there were times before, you can see back in this period over here in late April, late March and April. If I scroll down here, you guys can see the bottom axis, where it was a little bit flatter as well, maybe slightly rising. And it's interesting that during that era, there were also renewed USGS reports of magma possibly flowing to the Upper East Rift connector and Upper East Rift area, refilling that area all the way to Pool. So maybe that has something to do with that pattern, that shift of inflation source a little bit away from the summit and a little bit more to the south. Although it's not clear from the USGS update, we'll show you guys in a bit that perhaps the caldera source itself is shifting south, independent of that movement back and forth into the Upper East Rift connector and Upper East Rift zone. So we'll wait and see what comes of that. But that's the GPS line here. You do see quite a bit of variation up and down, right? And we've pointed out before that this up and down may in fact be mirroring these large deflation-inflation events, which are the most obvious signal if we look at the tilt record. And so here's a tilt record for the past month, and you see this blue line, there's a summit northwest of the summit at Uwekahuna. Down and up, deflation, inflation, deflation, inflation, deflation, inflation, big ones, little ones as well, but perhaps these bigger ones are the ones that are lasting long enough, multiple days, to reflect on the tilt signal or on the GPS signal we just saw as well. So that's the pattern there. As far as the shifting center of inflation, it might be useful to look at the map that comes on this page here. And so this is a map of the stations that we're actually measuring between. That GPS plot is measuring between Uwekahuna in the northwest and Crater Rim over here in the southeast. So we're measuring that distance right through there. And that works great if that spot right in the middle, right in there, if your inflation source is anywhere between these two spots, like in Halemaumau, then perfect. That shows you exactly what you need to know. But if that inflation source migrates to the south and it gets somewhere near the station over here, or worst case scenario over on this side of it, then this distance from here to here won't change because the spreading center is now going away from here and to there. And so that's just a little nuance, and we only have this Uwekahuna to Crater Rim automatic distance on GPS on the website. But there are other, you can essentially measure distance between any stations that are on a network. And this is done routinely in ESGS, and I'm sure that their internal monitors are showing them a different measure, right? Perhaps from Uwekahuna to Ahua, which is a station over here, which is outside of this great caldera outer crack of the collapse depression of the summit of Kilauea. So, in fact, you can see here is a plot we've shown before relating to the the connection or lack of connection between Kilauea and Mauna Loa. And not to look at the data itself, but just note, like, here they look Kilauea, they're measuring from Ahua to Uekahuna vertical to make sure that they don't get that little nuance effect there of things going to the southern part of the caldera. So that's just a little nuance, and perhaps that Ahua to Uekahuna line has been increasing all the way without showing this little feature. And that little feature may in fact just be within that one line, right, in that smaller caldera line. And if that is the case, and there's a lot of ifs going in now, this is all speculation, of course, but this is the game we play of helping us understand the workings of the volcanoes, the thought process of what could happen and why might it be happening and all that. So if that is the case, then if there is an increase here at the end, then you might be seeing the shifting back towards that middle part. So you might be seeing something like a buffering of the system where the magma we know is coming into the summit first, and when it fills enough, then it was able to send a pulse to the south, whether it's to the south caldera or to that upper east rift zone connector, and then shift the balance more to the south before it refills and then goes in pulses like that. So that's one possibility, and we'll have to wait and see, and that's why this is interesting, not just to me. So that is the GPS there. And I do want to point out that on the tilt, the deflation inflation in the last 2 days is really obscuring most of the signal here. If you look at the past week, you get a couple of them that are big and a couple of small ones superimposed on there as well. If that's exactly what they are, there could be some other process as well with that small magnitude there. You do see some of those bigger earthquakes come in as little spikes on a plot here. From far away, they can even send a signal onto the tilt meter. But no changes at the volcanoes from those distant earthquakes. Right, that's totally separate and independent. So to really try to dig at the trend in the tilt here, we have to look at this, perhaps try to ignore and filter out these deflation inflation events. And we thought that maybe about a month ago we might be having an increasing trend, something like that, coming up. And really, most of this month has been seemingly, we can't tell because of so many deflation inflation events, but it seems mostly flat here if we take the peaks of these values. Perhaps rising slightly with this most recent trend here, and so we await this current inflation end of the deflation inflation cycle that we're currently coming out of right now to complete, to really see if this comes up even higher or if it comes back down to this lower level over here and it ends up averaging itself out here. So it's very slow. Long-term changes are taking weeks to really even see what's going on, is how slow it's happening. But still changing, still shifting a little bit here, a little bit there, and that's the interest to us. It's worth noting, back to the GPS here, that if we go down to the Pu'u'o end of the line, that we do not see any obvious change in trend here. Maybe some small wiggles, right, the small up and small down all through here, but you gotta remember that this whole range of the Pu'u'o plot here is going from 0.02 to a minus 0.025 here, so it's about 0.05 in total is the scale of that one, which on this upper graph of Uekahuna, I know it's different places, different dynamics, but all of that fits entirely within one of these bars right in here. And so much smaller change there compared to what we're seeing, these swings here at Uekahuna would take up and down that entire lower graph we just saw. So no sign of it reaching Pu'u'o yet. We won't dive into those East Rift Zone signals again, since we've been doing that recently. But we will touch back on that here in future weeks. So we'll wait to see how that story develops there. And the source of all of this is a Kilauea update from the USGS HVO. And here it is, update from this past Tuesday. And I'll read it out of order here, but they do note 110 tons per day was the most recent measurement up to that point on June 30th. We saw a new point on the plot here just for maybe 2 days ago, adding to this text report. They do note here summit tilt meters recorded 2 deflation inflation cycles over the past week, along with continued gradual inflation. Continued inflation was also recorded by Summit GPS instruments. However, the pattern of tilt and GPS motions indicate that the inflation center may have shifted slightly to the southern part of the caldera. Seismicity has been slowly increasing in recent weeks, though has not yet reached levels seen immediately prior to the December 2020 eruption. So that's the message we've been giving you guys for weeks and months now. and just making sure you see that it's being reaffirmed here and is now sourced from the USGS. All right. Otherwise, no real change in the Hale Ma'u text, no real change in the East Rift Zone text here. In the activity summary, they do mention here no changes following yesterday's magnitude 5.2 earthquake north of Waipio Valley. So that's what we'll turn to next. This is our first tangent here before our break and questions about Kilauea and earthquakes. Before we say our thank yous and turn to Mauna Loa. But we'll turn to this 5.2 earthquake north of Waipio Valley. It wasn't the only one. But this one, 5.2, prompted a USGS information statement, July 5th, 1:43 p.m., and it was a depth of 17 miles below the sea. I'll show it on a map here shortly, but I will get to the next information statement that is a magnitude 4.2 earthquake. They only note one earthquake at 0.6 miles, or in fact there were two, but their statement doesn't include both of them there. So let's show you guys what's going on here. All right, the first one is up here in the north. This is 5.2 right here. So just north of Waipio Valley. Waipio Valley is right in here. These are the erosional valleys on Kohala volcano here in a northeast facing direction where the trade winds blow all that moisture in, and before it hits the crest of the eroded mountain over here, most of that rain falls off on that eastern side here. You can actually see the green east side here and the brown west side of the island here on this Google Earth image. I can zoom it in a little more for you guys, make it a little more obvious there. So anyways, offshore there, just offshore, but deeper down is where that earthquake occurred, 5.2. A couple little aftershocks there. You can see that one's right next to it was a 2.3, and that one is a 1.8 right in there. Okay, so if we move over here to the west, then we see this doublet here, two earthquakes. Maybe I'll change my background layers here since it's a little bit hard to see. Let's go to the ocean. Show you guys a little bit more where that is. Right off here off of the shelf. So two earthquakes here, both 4.2. One at a depth of 1 kilometer, but a second one that precedes it by a couple of seconds, a depth of 21 kilometers. That's closer to that 16, 15 mile range that we just mentioned before. So perhaps that deep one, it might be a flexure one, setting off some shallower structure there as well. And so there's all kinds of old cracks and things in the seafloor around here that can get reactivated when when the flexure and the readjustment of weight on the island can push them around. So let's look into that a little bit here. And so to do that, we're gonna use a series of Volcano Watch articles by the USGS. Most recent one here, back from February of 2019, by Brian Shiro. And this one is talking about why earthquakes occur so far offshore. And it's talking about this flexure-related, essentially the weight of the mountain here. So when the volcanoes are quite large and uneroded and still growing, as is the island of Hawaii, they exert a downward force, and the whole lithosphere, the crust of the earth, is bent downwards. It's deformed downwards. It's like lying on a waterbed or something like that, or lying on a mattress. So you do have quite a lot of bending stresses, right? Because this part of the crust is getting squeezed, and back over here it's getting pulled apart, right? Because that's the nature of the thing. So there's all kinds of deformation happening in there, and not just here, but there's a point back over here where it curves back to normal, where you have a similar kind of force again, where you have contraction here and extension up here, as you have curvature to return that semi-rigid crust back to its form, right? It's like a attenuated sine wave, something like that. So the idea being that you have this radius of around 100 kilometers off of this maximum load center where you have the most adjustment, right? So most of these flexure-related earthquakes can occur from that kind of force, and that can happen offshore off to the sides of the island as well, and even further off at smaller magnitudes. You can see here on the map the red ones being the flexure earthquakes that they've plotted, and they actually plot here on this one. They do plot 1871. They labeled a 6.8 on here, 6.8 in 1838, labeled as 6.8 as well, and an Oahu one as well. So, those could be one. That's one explanation. We'll look at an alternate here shortly. This is the thing that we typically refer to, and it's what the USGS refers to in their information statements as well. So there's a lot more in each of these Volcano Watch articles. Of course, I'm not going to have the time to go into every one of them in full depth, but I'm going to just show you guys, right? So that one was February 14th, 2019. We're going to go back to March 24th, 1995 now, and deep earthquakes and lithospheric flexure here. And once again, pointing out a series of earthquakes that occurred, right? And so I thought this was interesting just because back in 1995, they had a series of a sequence of earthquakes, and here you have it was March 19th, a 4.5, depth of 31 miles, deeper than what we had now, but not that far off of where we just saw that one right there. Right? And they had a couple of days before that, a magnitude 3 over here to the northeast of the islands, and not quite Waipio, but you can kind of see that these are somewhat in a line right there, right? And there is a 1871 magnitude 7, 1838 over here as well. And once again, talking about flexure as that one model. And one more example of this, a Volcano Watch article from April 14th, 2016, how earthquakes can happen not just near Hawaii Island, but also by the other islands as well. And so back in 2016, there was a week there where you had a 3.6 in central Maui. Then you had a 4.2 offshore east of Maui, and then a 2.8 in early April just offshore of Oahu, right? So noting that there could be these processes that whichever it is that are affecting the other islands as well. And especially when you look at that Lanai earthquake that's magnitude 7 or so, and how close it is to Oahu, where all the majority of our population density is, that's really a big hazard to consider. And this is one of the reasons I was wanted to talk about this today here. So let's get into this a little bit. So this is a map from NOAA. This is showing the age of the seafloor, colored here, and it's superimposed on that bathymetric map. And you guys can see here North America and Hawaii over here on the left side of the image, right over here, right? But what I wanted to point out is, if I zoom in a little more, you can see these lineations, right? This series of looks like cracks that go this way, this way, this way. Right? These are the fracture zones associated with the tectonic spreading of the Pacific Plate, which is source over here. It says the East Pacific Rise, where the magma comes out of this crack and pushes the Pacific Plate to the west over here. And where there are steps in that eruption area, you get these propagating long cracks that essentially are in the same place for millions of years and end up being weaknesses across the whole fabric of the Earth. And notably, this is the Molokai fracture zone right here that goes right across the middle of our islands, right through the middle of Maui and Molokai right through there. And so let's get some different views of this here. More spherical view here on the globe, and with the geoid superimposed, not that it matters, but you can see here Hawaiian archipelago, and right through here, this Molokai fracture zone. And you can kind of see that it's got a somewhat of a wedge shape right through here. We'll get back to this here in a little bit later on here. Not that we're going to spend too long, but that's going to be something to look at later. And here are the names of these features, right? So I don't know if you guys can all see this, but here's Hawaii down here at the bottom left, and the Molokai fracture zone, the Clarion fracture zone, the Clipperton fracture zone, the Mendocino fracture zone. These are all named known features important to the seafloor of the Earth. And if we superimpose some of these earthquakes, like 1871, 1938, on a trace of that Molokai fracture zone, they come pretty surprisingly close to right in there. Yeah, so it leads you to believe that maybe there's something else possibly happening there. There's another candidate explanation, at least. And there's a proposed Diamond Head Fault, which is still a little bit controversial, up in the air, as a possible splay, like a parallel feature over here. And as we pointed out, that fracture zone has some width to it, especially farther offshore here. So we'll come back to that here as well. But okay, so yeah, this image, just to make sure I credit it. Oh, no, come back. is from this paper by Anchieta et al. Seismicity around Hawaiian Islands recorded by the Plume Seismometer. So they actually put a bunch of ocean bottom seismometers prior to 2011, and that's where that data comes from, right? So you can see that they detect similar things as HVO network right here, but they also were able to detect a bunch of other events that were not in HVO capacity, right? And so some of those include areas around Maui and Oahu and Maui, perhaps I should say. All right, so, I wanted to point out that 1871 earthquake here is something that's been researched more recently. This is a 2020 paper by Rhett Butler and Seismological Research Letters here. And the important point here is that he is now proposing a revised magnitude 7.5 magnitude for this earthquake based on a synthesis of all the accounts and intensities and all the things, comparing it to other places. So we won't go into all the details of that, right? Except that you can note that there it is, on Lanai, that's 7.5, and once again, the Molokai fracture zone here, marked on a map, prominently in association as well. So another volcano watch, April 8th, 1999. Maui's 1938 earthquake in mind. That is January 22nd, 38, 10 p.m., magnitude 6.8 offshore of Maui. So landslides on the road to Hana. Communications were cut off for several days. Oil tanks shattered. Oil flowed into the sea. Water tanks at the ranches in southeast Maui all were damaged and leaking out. No lives lost and few injuries. No tsunami. But concrete cracking all the way to Lahaina, with a fire station tower in Kahului shifting half an inch there. Also notably 1938, I know I'm reading a bit some of it here for you guys, but I think it's worth it because this is some old information we haven't talked about. But it was felt in Kauai all the way to Big Island. Although Big Island people were more used to earthquakes, weren't quite as shell-shocked by the whole thing. But really on Oahu, rocks on roadways, plaster on buildings, and broken water pipes all across. But perhaps one of the more interesting things is that earthquake lights accompanied the 1938 earthquakes, right? During and immediately after the earthquake, intense bursts, glows, or flashes of white to bluish light lasting from a few seconds to about a minute were observed in many parts of Hawaii, even by campers as far away as Halape on a Big Island's south coast, 125 miles from the epicenter. So although there's no generally accepted scientific explanation for their occurrence, these lights apparently result from earthquake-induced oscillations or distortions in the atmosphere. So unrelated to volcanism, just an interesting thing there. I want to make sure just bring up some of these tangents because I'm sure that'll spurn some, maybe elicit some questions that we really can't answer. But there you have it. It's worth talking about and it's cool and all that. So, okay, Google Earth. Here is that Mendocino fracture, the Molokai fracture zone. I keep saying Mendocino. That's the one to the north. The Molokai one, you can see it clearly here in the west. It disappears here in the middle from the sediment of the Hawaiian Islands, essentially burying it, obscuring it there. And you see it again here to the east. And you can see that it's actually not just one line, but a series of many strands. They seem to kind of come together here, but that the southernmost strand, it comes suspiciously close here to this boundary, this north part of the Big Island. Right, you see there is that fracture zone strand right there, and here is that area of the Big Island, and perhaps somewhere in here might be some extension, who knows, right? But you certainly have to have suspicions that there could be a second plausible structure in there that's setting things off. So let's dive into this briefly as the last thing we do here. And it's worth mentioning, just to bring up a connection to our hotspot, Hawaiian Emperor Seamount Bend presentation we did a few months ago. At the time of the Hawaiian Emperor Bend, there was a change in the motion of the Pacific Plate that led this area of the musician seamounts here, the musicians, to have eruptions along similar kind of cracks that were tensional along the Murray fracture zone here. So there is a musician seamounts. Here's a Murray fracture zone right through here. You can see that there's these structures that actually leaked lava during that bending phase in a separate kind of process to what we're talking about today. But you see that more or less the range of deformation possible around these fracture zones here. It's pretty wide, right? So it's not unheard of to have some weakness that's parallel a little further away there. And continuing here. We're going to see this paper by Searle and all in 1993, and there's another proposed change to the Pacific Plate motion back around 83 million years ago. And so here's essentially the motion. You have a spreading center here where this is where the plate's getting lava coming up in the middle right through here, and it's moving away in both directions here. And it's also happening here and here, right? And so you have these offsets. These are the transform faults, these fracture zones that separate these strands of eruption here. And when a plate's moving in this direction, this way and this way, then that's their geometry. But as soon as that direction changes and becomes a little bit more oblique here and here, now you start having these strange geometries forming as a result of it. And so the actual angles and all that don't really matter as much. More importantly, focus on this image down here at the bottom, right? So how it might actually rotate and distort and cause some changes in the pattern there. And this is important because they are superimposing this on the pattern seen here east of our Hawaiian Islands right here. That kind of bend pattern we're seeing there, right? That kind of coming together. That's an interesting thing here. And so you see that this is clearly putting a fracture right here between Maui and Hawaii Island as a possible strand of that feature of the Molokai fault zone as well. Okay, so and one final just extra complication here, you know, you may actually have double, right? If you start saying, okay, well, this is actually a whole zone, and not just one single thing that's getting deflected. Now you can have all kinds of weird strand patterns in here. So when you start having this, and you have Hawaii Island somewhere in here, then certainly one of these strands could be in that range that we're seeing there. So that's the Molokai fracture zone here that I wanted to bring up, and it might fall somewhere right through there. And you can see here that you know, with a main strand somewhere through here, and maybe that range possibly coming out further, that you might suspect that this is somewhat in a line, and you know, you might think, oh, that's suggestive, but there's no link that we can point to here today, right? It's just suggestive of that trend, and interesting to see those two in that short interval, as we saw in previous reports as well. So I'm just going to finish off this segment here of the earthquakes and Kilauea by following up on a question that was asked last week. I believe it was Marin who was asking about when we see these earthquakes, what is the size of the area that's actually rupturing, right? So I came to paper here in Wells and Coppersmith, 1994. Magnitude on the left here, and rupture area over here on the bottom. So this is in square kilometers, and you can see that if you have magnitude 7, you might have somewhere in a range of 1,000 square kilometers. Might be the actual area that it's moving, right? And different kind of faults have slightly different patterns, but more or less generally the same. Magnitude 5 earthquake, you might have an area of 10 square kilometers actually rupturing, right? So think of it as like a 3K by 3K area. But how much is that area moving? So if we look at another figure here, the average displacement, right, as a function of magnitude as well, you can see that for magnitude 5, you're looking at somewhere in a range of 10 to the minus 2 meters. That's a centimeter, perhaps. I don't know, a centimeter or so. Maybe less than that even, you know, is what you're looking at. Whereas if you're looking at a magnitude 7, now you're looking at a range of 1 meter, several meters. That's the amount of motion you're talking about. So 1 meter over a 1,000 square kilometer area, or something more like 1 centimeter over a 10 square kilometer area, something like that, right? And to maybe put this a little bit more at reference, we can come back to what we saw in 2018, magnitude 6.9, motion of that was on May 4th associated with eruption in Lower Puna. And they've modeled here everything in this dark blue area as that patch, the area that slipped in that essentially magnitude 7 earthquake right there. So we talked about it being about 1,000 square kilometers there, right? So you're seeing it looks like it's maybe 30 kilometers long here by maybe 20 kilometers that way, right? So 600 square kilometers, somewhere in that range. That's ballpark it. And magnitude of slip in meters here, you can see that their maximum was a little bit over 5 meters. And so maybe your average is somewhere around 3 meters, 2.5 meters, something like that. And so in a few meters, that's kind of how it fits in there as well. So that's what the big ones are like. you try to imagine what these magnitude 5s or 4s are doing, right? If magnitude 4 would be even less, magnitude 4 would be way back. Maybe it's moving a millimeter over, what's our previous? Over, what would that be here? Square meter or something like that, right? So that's how it increases exponentially there. So hopefully that gives you a better idea of what's actually moving when we're looking at earthquakes, and ties it all together for you guys here of what might be happening underground there, deep underground. So we'll take our first break here. We'll say our first thank yous. I just want to start off by talking about HawaiiTracker.com and pass it over to Dane here.
Right. So before we get into our thank yous, I just want to encourage people, if you do have any questions, especially about Kilauea and the recent earthquakes, go ahead and put them in the chat and we'll get them answered here momentarily after we shout out some of our sponsors and HawaiiTracker.com. So we are brought to you by HawaiiTracker.com. Best way to support this type of broadcast, if you appreciate it, is just to share this video into your own social media network. Help get more eyes on it. Really helps the channel grow. We also are building a community on HawaiiTracker.com, so you can become a member there and join that community as well. And then also we are taking donations if you feel like supporting us monetarily on YouTube through Super Chats, but also on HawaiiTrackers.com/support, where we take all kinds of donations. That also really helps us keep this type of content coming. We do want to thank our sponsors. We have a couple sponsors that have been with us for a little while now. First is Kaleo's Bar and Grill in the heart of Pahoa, doing some unique twists on some traditional dishes, adding a little bit of local flair to them. They got indoor, outdoor dining, COVID-safe policies, takeout. Really a great place to go for locals or for visitors. So if you're out here in Puna looking for a place to eat, we'd recommend checking out Kaleo's. Really good spot, good people, good service. So yeah, the place to be right there. And also, we want to thank Kalani Tours. Kalani Tours does several different kinds of tours, focusing primarily on the volcano, waterfall tours, and also a Kona Coffee Farm tour. The deal with the Kalani Tours is that they do more intimate, more small groups, as opposed to the giant tour companies that load everybody up on a bus and shuffle them around. This is a little bit more personal, more educational, and they kind of help keep things Pono as far as the tourism side of things goes, especially with so many visitors out on the islands now. Keeping things Pono is really important, and we appreciate their support as well. We also are brought to you by the Puna Strong grant, which was given through the Hawaii Community Foundation. We thank them for their support. And with that, I think we can get into some questions unless you have something to add to that.
Yeah, no, that's all. Yeah, thank you guys. And of course, we have a lot of small donors that we will shout out at some point as well. And thank you guys all for your support, and Kane'e Hawaii as well. Mahalo.
Right. We do have a $5 super chat from Andre. We appreciate that one. Thank you. No comment. So let's get into some questions here. This one pretty general, but Sharon asks, is it safe to say that even without an active eruption, magma is constantly moving underneath the volcano?
That's our working model, especially for Kilauea and Mauna Loa as well. I mean, Mauna Loa maybe a little bit less so, in the sense that we saw eruption decrease in 1950 to 75 kind of thing, right? But prior to 1950, yes, absolutely so. And maybe we're doing something a little bit different. Magma is still moving inside of there, but more so more recently than it was. So it does vary a little bit in longer term patterns. Certainly Kilauea hasn't varied a whole lot in our lifetimes here. It's been, all the time moving underneath there. It's just a matter of where exactly, right? So it was moving from the summit to Pu'o'o for a lot of that time, and then it moved all the way to Leilani, and then it backed all the way up to just Halemaumau, and so now it seems like the summit and Upper East Rift is the area of the where.
River asks, does an increase in gas usually precede lava reaching the surface, or could just be a migration?
Yeah, it's thought so. There's a lot. It's yes. Increasing gas does usually precede lava reaching the surface. There is more nuance to it because there's more than one kind of gas coming out, right? So You could say that when you see the SO2 that we most often report on spiking, the magma is getting pretty shallow for that to actually happen in a short lead up to an eruption, more than likely, right? So when we see that coming up, that's a short-term indicator. You could also look at the CO2 to SO2 ratio as a long-term indicator of magma supply, of how much fresh magma is coming in from depth, because the CO2 comes out from the magma much deeper down than the SO2. SO2 can stay dissolved up until that point where magma is about to break to the surface kind of thing, whereas the CO2 comes up as magma is coming into the bottom part of the volcano. So if you see the CO2 ratio come up, then you might say, well, there's more source at depth, and then how does that propagate into the upper parts? That's a whole other question, but you can see that as well. And so it was detected prior to the 2008 opening of the overlook vent at Halemaumau. They detected back, I want to say a few months ahead of time, increased gas emissions from that area, and that's where the vent opened up eventually. So certainly that's something we look for as an indication of it coming to the surface, the SO2, but also we haven't heard much recently about the CO2, and there's a lot of detail in there that we'd love to hear.
There was also one little addition thing I'd like to throw in there from 2018, where we saw when the lava had come through the water table, the first thing that you would get out of the cracks was steam, right? As it was trying to intrude through there. So you see these billows of steam coming out or start to come out. And then the SO2 started to come out, and then the lava. Mm-hmm. Right? So when it has to come through that water table, you just get that little bit of extra nuance in there.
Yeah, absolutely. It's absolutely true. Yeah. And of course, that doesn't always happen in a summit. If you've already burned through the water table, then you can kind of skip that step, right? We didn't do it in 2018. But if we have a rejuvenation of the west vent or some other fissure in a summit area near that recent eruption site, we may not have that steaming phase as much because the water is not back there yet. Yeah, great point.
Carl asked kind of the question that's on a lot of people's minds. Is there any indication of a renewed eruption, and do you think the caldera will be the next eruption spot?
No and yes. No indications of a renewed eruption. In the short term right now, I mean, it's got its steady activity. I do think it's just a matter of time before it does it, but it's not looking like it's going to do it this week or this month right now. And as far as the caldera, that seems the most likely place. I mean, if you were Vegas, that would be the biggest pot right there. So Upper East Rift also being a secondary possibility there, within range of the caldera still too. I consider that near caldera as well. So yes.
I have one final question here for this segment. It's not exactly on Kilauea or Mauna Loa or Hawaii volcanoes, but it's about the news that we've seen recently. Can you describe what is a mud volcano?
All right. So
about those?
Yeah, mud volcano. Yeah, it's very just briefly. I mean, it's not something that's erupting lava, right? But it is erupting a fluid, which often can be gas or mobilized liquefied sediment, right? That comes up, and yeah, very very often in Azerbaijan, the land of mud volcanoes, where they have thousands of these things over there. Yeah. So yeah, that's basically it. It's like an instability in the strata there, right, where you have something that's less buoyant that's been trapped down in the strata for some time, and whether that layer above it becomes weaker or becomes more fluid, or if it's something like a sediment, if it becomes permeated with something, whether it's water or some other gas enough to be able to move, then you can have that massive essentially eruption as a release of a big bubble that comes up from depth, right? And so it's no coincidence that there's a lot of oil and gas exploration and prospecting in that same area.
And aren't they considerably cooler as well, the temperature of the things?
Yeah, absolutely. Yeah, because it's not actually a molten rock. It's
right.
Like a liquefied rock, right? It's a liquefied solid sediment, right? Where like liquefaction is just the ability for something to flow as a fluid rather than it actually melting into a fluid. So yeah, they're essentially, because it is gas and it can ignite, it certainly can be hot, but it's nothing like lava. Yeah, it's a good point.
If anybody wants to learn more about mud volcanoes, I'd recommend checking out Mark Tingay on Twitter. I'll go ahead and drop his Twitter handle in the chat. He's kind of the mud volcano specialist. And this is like the day he's been waiting for was, some mud volcano to make international news. So he'll answer any of your questions there.
Yeah, it's a fantastic resource. He's really on his stuff. It's worth checking out, right? And it's worth noting that research on these phenomena have been happening for decades already, and new era of social media. As soon as it gets the social media attention, then you can then start pulling from all these old historical studies, as we do all the time here, and that's what's fascinating about that. Yes, check it out.
And we have a $10 super chat from T. Laus. No comment, and I really appreciate that as well. Thank you, guys. And I believe we're on to the next segment with that.
All right. Mahalo, guys. So our next segment is gonna be Mauna Loa, and we're gonna start with just a quick review of the signals here before we turn to Volcano Watch in 1975 eruption and some of the details of that. So we'll start off with the actual text update from the USGS here, because there's not a whole lot of change, and this is where we get our most of our detail recently. So not erupting, slightly elevated seismicity, no significant changes, no increased hazard. That's the bottom line. During the past week, 147 small magnitude earthquakes below magnitude 2.5 below Mauna Loa. Of these, 46 beneath the summit. That's a little bit lower than last week, so down a little bit. Summit and upper elevation flanks, and 90 underneath the southeast flank. So still more under the southeast flank, also down a little bit, but that's the same essentially pattern there. Maybe slightly less at the summit, but ongoing still under the southeast flank, and all still in the same areas, shallow depths less than 5 miles below sea level. Slow rates of deformation, and no other changes there. So that's the real interesting thing here, is this 46-90 split summit to southeast flank, because when we go to our normal Mauna Loa earthquakes map that looks at just the summit region, you see not a whole lot. So here is those 46. If you look at it here, 46 is what shows in this top label up here for the summit area right in there. That's the 46 there for the past week. And when we look at these earthquake rate plots, this also based just on that summit area there. So here's our 46 for the last week right in here. You can see that over as far as per day, there was that little flurry that happened about a week ago near that northwest of the summit. And really it's been low since then, maybe a little bit over here, but really we haven't exceeded 15 earthquakes per day. So that's really, it's maybe slightly elevated, barely. It's really getting pretty low again, going through these bursts essentially there. Yeah. Back to the past year, you can see here we are, pretty low constant levels after those I'll call them bursts again that we saw here earlier in the year. A couple of different ramp ups in activity that lasted several weeks before coming back down. All right, so really here we are. We're just still waiting for something to happen. It's going in slow motion there. If we look at the earthquakes on the USGS map here, we can see that Kilauea is down over here. That's Pahala, it's separate. There's our little bit still northwest, a little bit still here in the southwest flank. And maybe we could cluster maybe these ones over here being those southeast flank earthquakes that are popping up above the threshold on this map. So we have a 2.4 at 6 kilometers depth. We have a 1.9. We have a 2.3. We have a 1.9, 2.3, and a 1.1 there. So those are the ones that are the largest of that set. And you imagine that all those other 90 are going to be somewhere in there, not showing up on this map because they're just too small to show up here, but they're getting counted in that plot. So that's where they are. Same pattern, southeast flank of Mauna Loa adjusting. And that's been our question the whole time is are we in a new phase where magma can continually come into Mauna Loa, still steady state now, and the south flank just moves out of the way and essentially it emplaces underground without having to erupt because this flank is so mobile, right? We've talked about how often there's a big earthquake that precedes an eruption, and that means that the flank has to be locked in order to actually break that much. You'd think somewhere it's got to catch. and we're not seeing any obvious sign of that quite yet, although maybe it's moving more so in one area than another. We'll have to wait and see how that actually plays out. So not a whole lot of change in the patterns right there on Mauna Loa. Looking at the tilt and GPS data, let's go down to the GPS first and look at that cross caldera distance length, and it's not changed here. This is, we can see there's been a lot of variation. This is why we have to wait for after time passes to really get the true trend and not jump to conclusions about these extra points up and down here. So the average value really hasn't changed a whole lot, even though we still have ups and downs here within that range of noise. All right, so not a whole lot of change. If we look at the tilt for the last month, we do see that there is some changes happening here. Maybe there's a little bit of undulation, but there's also seems to be some larger variations here. Maybe 1 microradian to minus 1.5 microradian total. That's about the size of that tilt signal we saw before on Mauna Loa. And there is no indication that this has anything to do with with a magma. It could be, it could not be, and it's unclear, which is why we don't often talk about tilt on Mauna Loa as much as a giveaway. We need a much bigger signal than what seems to be the natural variability that we see here, that we can't really tie to anything else here. So it's just a chance to point out why we don't use a tilt as much in Mauna Loa, and why a signal like this is not something we can use to jump to any conclusions, especially we don't see any other changes anywhere else. All right, so that's the signals from Mauna Loa, and that really wraps it up. So we're going to spend the rest of our time on our discussion today on the topic brought up by this week's Volcano Watch, published today, remembering Mauna Loa's eruption on July 5th to 6th, 1975. So 46 years ago this week, this is the anniversary of that less than 24-hour eruption, a 20-hour event with vents confined to the summit region, area above 12,000 feet or so. Right, so that summit region does include a little bit outside the caldera, but above 12,000 feet, that's essentially that cutoff zone because of the pattern of eruption there. So at the time, this was the first eruption in 25 years, which had been the longest stretch since 1843. We've since passed that at 37 years and counting right now. So I won't read everything, but we're going to essentially go into detail about this eruption here, so I'll pull out the important things here. It's the first eruption monitored by modern instruments, so we do have modern data, although modern with an asterisk, because 1975 modern is different from 2021 modern. So data quality is an issue, and the data sets are not exactly the same from then to now. Still, we do have more data than anything before that. And it is a typical eruption occurred only within that summit region. So they note here, all of Mauna Loa's 33 eruptions since 1843 have started at the summit. And of those, about half were only in a summit region, like in 75. So 75 could be an example of that half of the eruptions on Mauna Loa that begin in a summit and just stay in a summit and then end in a summit, and that's all you see. All right, so we'll focus just on that little sliver for now to start, and we'll expand from there a little bit later on. But the important things here is that unrest began clearly in April 74, and so over a year in advance, with large seismic swarms in August and December 74. Right, so April, August, December, you can see that there's a few months of activity, and months in between without, month with activity, months in between without. But there are counts with a threshold of let's say 1.7, right, and things above 1.7, of about 450 earthquakes per day in August, and to December 1,500 earthquakes per day above magnitude 7. This is in December. This ended up being 6 months ahead of the eruption, right? 1,500 per day above magnitude 1.7. So to kind of step out of it here, recently in 2020, 2021, we've seen increased activity, but not to this volume right here, right? Not 1,500 earthquakes larger than magnitude 1.7. So, but the week before that was actually fairly quiet, and then that night of July 5th, at just before 11 p.m., they noted the activity escalating on the seismographs, and within half an hour, 40 minutes or so, they notified eruption was imminent, and it began about an hour after that. So it was over by 7:30 p.m. the following day. So the staff arrived at the summit area 2 hours after eruption began. They actually got there by airplane. And we'll get into that here in a little bit as well. And fountains were extending across the caldera to about half mile southwest outside the caldera, and flows going west and southeast. A few hours later, on July 6th, in the early morning, 2 a.m., fissures opened up across North Pit and northeast of the caldera and started going northeast as well. I will show you guys some maps here shortly. I'm just going to make sure we get to the Volcano Watch here first. And that is essentially the short version of the eruption there. 7:15 a.m., the fountains stopped erupting, and the flows kind of petered out by later that evening there. So there was activity, seismic activity, for about a week afterwards, as there was a flurry of migration of earthquakes from the summit northeast to the northeast rift zone. And they did not know if that would actually erupt at the time, but after about a week or so, it quieted down, and it did not erupt until 1984, which it did from that exact spot, in fact. So that was an indication for the future eruption, the next eruption that was a summit to flank sequence as well. So we'll look at that as well. But some stats here. They say of the 14 summit-only eruptions for which we know the start and end date, 1/5 lasted a day or less. Only one lasted a week or less. 1/4 lasted between 1 and 4 weeks. And 1/3, 5 of them lasted between 1 and 6 months, with one lasting several years. So they can really go from less than a day all the way to several years. And there was really no distinct pattern there, right? With 1/3 of them up to 6 months, and 1/3 less than that there, yeah. So no exact patterns there, but they do note here that they don't know when the next eruption will be, and the eruption will start at the summit if it follows a pattern set by eruptions since 1843. So that's the expectation: start at the summit, and then either stay at the summit, like 75, or migrate down a flank. Before the eruption, we expect weeks to months of unrest with a rapid escalation of seismic activity immediately prior to the eruption. As our monitoring network is more extensive and sophisticated in 1975, we also expect higher overall earthquake counts. So that is the USGS statement here on where we are and what to expect leading up to the eruption here. So that's the Volcano Watch released just today, on July 8th, 2021. And I want to show you guys some of these pictures here. So this is Don Peterson's image, aerial image here, presumably from an airplane. Looking north, Mauna Kea is here on the horizon, and you can see here the fissures in the northeast rift zone, sending lava flows down to the northeast here. 1975, there's one image. Slightly different view here, looking a little bit more from the south. Here's the summit caldera, and fissures began up here in the middle, also to the southwest, before they also later on migrated over here to the east. And here are these northeast upper northeast rift zone / summit fissures that were feeding that flow to the northeast there. Yeah. The early mornings of July 6th there. And a little bit of close-up of one of these fissure lines, and a little bit of a spatter rampart, and you can see some cinder cone forming around here as well. And so that eruption, of course, only lasted 20 hours, so you don't really see the development of larger features like cinder cones or lava lakes or any of that kind of thing. It's just flowing downhill and some spatter ramparts, and that's basically it there as far as the features that are left, right? Lava flows as well. And so source of a couple of these is Volcano Watch from July 1st, 2010. And this gives a little bit more of a human story of it, right? Talking about how Hawaii Volcanoes National Park Ranger Bill Fink was wide awake with all other 10 hikers in the cabin at Red Hill Pu'u'ula cabin in the northeast flank of Mauna Loa National Park here, and they all woke up and saw the glow of eruption on the horizon there. So they actually were monitoring from there, looking at the horizon. They really couldn't see the eruption source. They could just see the glow from that campsite there. But USGS scientists did get in the airplane there. Yeah, I'm not quite sure if it was Jack Lockwood who was piloting that particular flight. I believe that may have been the case, as he is known to have piloted for some of those eruptions there on the HVO staff, and also a very accomplished Mauna Loa researcher as well. So there's where these images come from. So they had seen some more story from this Volcano Watch. They had seen increasing signs of seismicity April throughout the year here. So they actually saw that there was increased eruption potential. So they installed more monitoring instruments on the volcano in 1975, including, I want to say, 3 new tilt meters, one of which was quickly buried by lava. So didn't get to keep them all. But they did see something building up to it for months ahead of time. So a couple things worth reading for you guys here. Surprisingly, in a week prior to the eruption, daily earthquake counts were relatively low. But shallow seismicity increased sharply in that evening there. So let's scan down here a little bit more, and here we go. By 1:50 a.m., July 6th, HVO scientists were flying over the summit in a light plane here for direct observation of the eruption. So they noted there at that point in time, of course, that's how they had to get there. You can't really hike up that quick, and you don't know where the lava is flowing down at those upper elevations. You don't have to cut off your path. That's something to consider. So the aircraft was well used even in 75 there. So of course we have other older eruptions in Mauna Loa also documented by aircraft as well, whether it be Air Force or military or scientists as well. So long history of aerial reconnaissance in Mauna Loa here. In any case, 65 to 130 foot high fountains of lava, 20 to 40 meters high, across the length of Mokuāweo Vale and over to the southwest. Lava had flooded more than half the caldera floor and was cascading into 3 pit craters in the upper southwest rift zone. So let's see, there is a picture of this here somewhere. See if I can find out where it was. Maybe did I lose it here? Let's come back. Oh, I don't have it here quite yet. So, well, let's show you guys this one here. Here's where the lava flow came down in 75, all the way down to close to the Forward Drive Road, just uphill from the Weather Observatory Road. So here's the edge of the flow right through here. And that's about as far as I got close to that road, right in there. So that's that lower extent of it right in there. And I'll find that picture somewhere. It'll pop up here again for me somewhere. I think I have it here somewhere. Yes, Dan.
It's always just a massacre of tabs. Like trying to pick through them all. Which ones is it?
Yeah, sometimes I do miss. Yeah, I would have so many images I want to share that sometimes one does slip through here or there. And so maybe it's coming up here later on. But oh yes, I know. Yeah, I know where it's coming up. Here, I will find it. We're going to talk about this paper by Jack Lockwood et al. Of Mauna Loa activity, and let me jump down here since we're talking about the lava flowing in the pit craters and show you guys what that might have looked like if I can reach it here. I think it's in this paper. Maybe not. Somewhere. I must have passed it already. Yeah, anyway, spectacular lava flowing into the craters. This is perhaps the best photograph I've seen, which is why I'd like to find it to share with you guys. There it is, right there. Aerial view of lava cascades into Luaho Upper Southwest Rift, 2:40 Hawaiian Standard Time. Cascade height about 90 meters, so over 200 feet there, 250 feet or so. RT Holcomb photographer there. Right there, lava coming down over the edge, pouring into that pit. Right over there, over the edge, right in there. So that is what I wanted to show you guys right in there. So Otherwise, we can, I think, wrap up this particular Volcano Watch article right in here. Lava overran parts of the summit hiking and jeep trails, but did not cut off the Mauna Loa Observatory Road. So that's the interesting story there. Of course, as magma moved into the northeast flank after the eruption was over, the park ranger Fink was still stationed at that cabin and had to be evacuated because the earthquakes were all coming closer and closer to him and happening every minute or so as he was monitoring the area over there. So, all right, let me come back up here and let's do this a little bit more properly. This is the one of the more comprehensive summary papers of that Mauna Loa 75 activity, tied to what happened later in '84 a little bit. And so by Lockwood et al., this is from Russian paper 1350 from the USGS that was celebrating, I forget which anniversary of the volcano observatory there, or the eruption here. So in any case, Diamond Jubilee HVO 1987, I think that was what it was. All right, so we'll read through everything here, but here's a plot of those earthquakes, right? So you can see here 74, 75, number of earthquakes per day is what's actually showing here. So you see that in April 74 it ramped up, came down, it had a couple of spikes, right? And then they actually had a big spike in December, right through here, right? And it's worth noting that in December, I'm going to scroll up here to the abstract, because in December we actually had an earthquake, a big earthquake that was the perhaps the warning that more was to come, right? And so maybe I'll come back to that here a little later. I don't have that earthquake right in front of me. But you see that we actually had these, they're actually referring to them as bursts, coming up here and up in here, and there is eruption right in there, with some quiet times in between, right? So this is 2 full years of data. So if we were to compare that to what we're seeing today, we're not really anywhere up near to these 1,500 per day volumes. We're maybe more in this range of stuff, like right through here, perhaps, right? Might be the pattern we're seeing. So there might be still more to come, and we expect to see higher counts, as well as earthquakes that set off one of the flanks as that kind of I don't know what exactly is the right word there. My words are failing me. It's that indicator that there's more to come. Dane? Oh, I can't hear you. There you are.
Microphone wouldn't unmute there. I was just saying I was going to hop in and throw words around to see if I could get you the right one.
Yeah, thanks. Yeah. All right. Well, onwards, and we've gone through this a little bit here. One interesting thing I wanted to point out here. This is a picture of pit craters in the upper southwest of Mauna Loa in April 1975. This is Lua Hole in the lower right corner here. This is that pit crater I just showed you guys that lava was flowing into. Those summit fissures came across here and over here, and then were flowing into the pit crater right there. But they're showing how much snow there was up in the upper southwest rift in April 75, and you might see that maybe there is possible anomalous melting. Maybe there is a lack of snow in some of these areas because it's hot underground. There and perhaps there as well, right? The most obvious places of where you might see missing snow were perhaps because the ground is hotter there. So that's something that was noted back in April 75 that we have not mentioned yet. And so they installed more survey networks in the lower elevations in the summit. They were cataloging earthquakes more meticulously, and during the week of June 30th to July 4th, 3 borehole tilt meters were installed on the summit and north flank. One of these tilt meters was to be destroyed by lava flow in a few hours before final adjustments could be made. And there's where that information comes from. So we've talked about the eruption sequence a little bit as well. Here are the earthquakes that were leading up to that eruption in July of 75. So you can see that there are similar earthquakes northwest, a little bit of a cluster to the north here a little bit too, and this large cloud of shallower stuff here underneath a summit and upper southwest rift, just as we see today. And these ones being more intermediate in depth, just as we see today as well. That's what squares are indicating here, as opposed to the plus signs here. All right? So similar pattern of earthquakes, and possibility for renewed activity, as they say here. July 7th to 12th was a period of great public concern as an outbreak of lava lower along the northeast rift zone seemed possible in light of both the ongoing seismicity and the numerous historical examples of brief summit eruptions, followed within a few days by flank outbreaks, for example, April 1942. So they knew that magma was going into that middle northeast rift zone from July 6th to 12th, with several hundred small earthquakes daily within the northeast rift zone, dozens of which felt, concentrated all in one area just southeast of Pu'u Ula Ula, Red Hill Cabin, where the ranger was stationed. And they measured dilation in the area there, so they know that magma had come into the area. But July 10th and onwards, the tremor diminished and everything wound down to a halt and would not erupt until 1984. Now, they had actually had postulated that it might be sooner than that, but the 75 South Flank earthquake of Kilauea at Kalapana, I think maybe, as I mentioned in the past, may have delayed some of that as well. So that caused them to be off, but here we get some additional images here of those fissures in the upper southwest rift zone here. Once again, early July 6, 1975. All right, here's a map of 1975 flows and the fissure lines. So this darker pink, that's where the fissures were, right? Across the entire summit of Mokuʻa right? Kind of two trends. One, it trends northeast this way, and a junction right in the middle, and one different trend to the southwest over here that went all the way outside of the caldera, all the way to Luaho by South Pit over here, right? So that's the crater the lava is flowing into right here at the bottom over here. And up here to the right, here's Mauna Loa Observatory Road, and that's that little edge of the lava flow that came close to it up there at that northern tip over there. Right? That's the pattern of it, and you can see that it covered almost all of the bottom of Mokuʻa caldera right through here. Not all of North Pit or South Pit, but most of the actual main caldera itself right through here, apart from the high cones, 1949 and 1940 cones, obviously, and other high spots in there. But as mentioned in this week's Volcano Watch, 90% of this eruption was covered by the 84 activity. So we'll show you guys a map a little bit later on that shows how it stands today, with 84 covering a lot of this stuff and what's left now. Okay, so this is the earthquakes pattern during and after the eruption here. So they actually note that the earthquakes that were west of about here, so all of these ones, this is the before the eruption, was actually fairly quiet, a little bit and a little bit and a little bit, but really nothing like the level was before it actually fissured open, all through here, right? And then after the eruption was over, the activity moved to over this way, and so all this over here in this area is all after the eruption was over, and you can see why they were so concerned, right? You see essentially along the northeast rift and maybe the south flank Mauna Loa area below it, allowing movement so that this stuff can come into there. Right? So you see that magma clearly moved from the summit over here to the northeast rift. And I didn't know if it was going to erupt right then and there, or what actually happened is it waited to 1984 to come out of this similar area right through here, mobilizing that same magma pathway there. We won't talk about 84 too much, only in as far as it relates to the 75 and how it fits together here. So they had noted here the pattern between summit eruptions only and then flank eruptions with different intervals of time. So May 49 before flank eruptions, and 51 and 52 over here. with a gap of about 2 years or so. Sometimes you have a gap of only a few months, like in 1880. Here's another few years one again. Right, so they thought that after 75, that maybe somewhere in there you might have, after a couple years, somewhere in there you might have another eruption again. And that would have put it somewhere in the late 70s, but it took another 6 years beyond what they predicted till 84 for it to happen, perhaps because of that late 1975, November 75 Kalapana earthquake, magnitude 7.7 by some calculations, revised since then. All right, so that's the pattern here. And that's something to think about in the future as well, is that you often do have a pattern, not always, but you often have a pattern of a summit-only event, and then you have an event that's summit and flank combined into one that follows after some time. So because our last eruption was on the flank, you might expect the next one to be one of these summit-only events. We'll have to wait and see, of course. That would be the default expectation there. And then after some time, you'd have another summit, and then moving to the flank again. And we would expect it to be the southwest rift zone the next time, since they often alternate as well. Okay, so we've shown this image before as well. This is all the earthquakes from 1962 to 1984, and this line of A to A prime here is this cross section going across this. So looking at depth, we have this pattern of the shallow earthquakes around the summit and upper southwest rift, and over to the northwest, this area to the side. So with a magma body postulated to be somewhere in here like this, with some feeder source farther down like that, right? And that's where the patterns we see today and how that all fits together, and why we've been talking about all this context, because we're seeing the same patterns today and the same sequences. We're just not seeing the numbers that we were seeing before from 75. So I'm going to skip down. I'm going to go through a lot of 84 stuff, but I do want to point out this plot here. This is cumulative number. This is earthquake numbers, earthquake counts split into shallow, 0 to 5 kilometers depth, intermediate, 5 to 13 down, and deep earthquakes. So eruptions happen here and here, and you might note that the deep earthquakes don't really change at all. Deep earthquakes are uncorrelated to anything with eruptions. You look at the intermediate and the shallow ones as what you look at. And what you might note is intermediates might come in a little bit sooner than a shallow, and it might be associated with some of these flank earthquakes, like the 6.6 right through here, and the other one that's not quite mentioned, not drawn on this plot, but perhaps right in here might be where that other earthquake lands in, I want to say December of 74. And we'll look at that here shortly as well, too. So this paper goes into 84, so I'm going to scroll down here and just point out, here's that diagram, magma, body, and feeder zone, earthquakes to the side and above as before. We're only going to look at the 75 stuff in relation to the 84 eruption. So here is the 84 fissures fuming. I'm sorry, the 75 fissures fuming prior to the 84 eruption. And here's a 1940 cone that survived the 75 eruption. Lava flowed all around it, right, but didn't quite cover that little high spot. And this here is all 84, so we'll go past 84. We'll look at this image here. We've seen it before as well. So the 84 fissure comes across the middle here, and it cuts off the 75 fissure right through here, and actually in 84 buries all the lava that was put into the main summit caldera in 1975. Okay, just a little bit more here. I want to show you guys that last map here. So okay, here is the before 84. This is the 75 fissures here with all that lava that came out of that northeast rift near the summit, right up there. And you can see 1984, you don't even see that pattern. Everything is covered from the northeast rift eruption in 84. So easier to see in a map form. So let me get down to where that is shown as the last thing to show you guys in here. And there it is. 84 is in pink and 75 is in blue. Right? So you see that within the caldera here, just a little bit of blue towards North Pit and a northern edge, northwest and northeastern edges here. You get a little bit of it over here by the Northeast Rift, a couple little strands, and easiest to see by the Mauna Loa Observatory Road, actually, way up there. 75 is a lot easier to get to than 84, which is easier to access. Perhaps over here when you hike up the Mauna Loa Trail in the National Park. So you can see there what is left. Little patches of blue, 10% of it left uncovered compared to before. An 84 eruption there. All right, so that's the story of 1975, and one final thing a couple final things here to talk about. I did say that often there is a summit and then flying sequence, so I wanted to point out from a separate paper in that same volume by Lockwood and Lippman. Up here is summit eruptions since the 1820 era. Right, so you see them much more frequent. These are the half of the events of Mauna Loa at the summit. That's all of this up at the top box over here. Right, so you can see that you often have a summit. Then you might have something on one of the sides, Northeast Rift Zone, Southwest Rift Zone, in this case, radial vent to the northwest here. So we actually had summit, Northeast Rift Zone, radial vent. Summit, Northeast Rift, Summit, Northeast Rift, Summit, Southwest Rift, Summit, Northeast Rift, Summit, Southwest Rift, Summit, Northeast Rift, Summit, Southwest Rift. So it's not a clean pattern, but that's where this comes from, this idea that there might be some patterns in here, right? And so I show you this so you can see the natural variance as well. So even though we see that it should follow this pattern, it's not always so clean, and you might have something a little bit, you're always going to be on alert for it to break the pattern as well. Pattern, of course, is what we have to work with and what guides us, so I want to make sure to show it to you guys in this level of detail at least once here. And last thing, revisit this volcano watch from July 2011. Mauna Loa's 1975 eruption in terms of today's volcano alert level. Right, so they actually note here that I'll skip all the sequence once again, but they do say that even with the lower capabilities of detection in 1975, they might actually have in April noted a clear increase in daily earthquake counts, and they might have put the alert level of the volcano at that point up to an advisory alert level and yellow aviation color code, as we have today on the volcano, in fact, right? Similar to today. So April of 74, they would have gone into yellow and advisory and kept it at that way as persistent earthquakes occurred all the way through. All the way through fall 74. And here we go. On November 30th, 1974, magnitude 5.4 earthquake occurred in a Kauiki fault system underneath the southeast flank. So I was wrong, it wasn't December, it was in November 30th, 74. And that was the one that associates with that spike of earthquakes and that shift in a pattern or ramping up towards an eruption. That was that alert, that indicator, right? The harbinger of eruption to come there. So they say that earthquake alone may not have warranted elevating alert level and code from advisory yellow to watch orange, but combined with the fact that in early December, earthquake counts jumped from 100 to 200 per day to over 1,000 per day, that might have been enough at that point to go to advisory, from advisory yellow to watch orange right in there. Especially when you add in that on December 15th, there was a 4.6 shallow underneath the summit, and daily earthquake counts peaked at 1 per minute, almost 1,500 per day. So if not in early December, then certainly by December 15th, they would have gone up to orange, and that's the pattern we can expect from Mauna Loa and USGS today, we would hope, we'd expect as well. So a second shallow magnitude 4 earthquake beneath the southeast summit region on March 26, 75, and thereafter an apparently accelerating rate of shallow magnitude 3 plus earthquakes beneath the summit would have provided additional basis to change volcano alert level and aviation color code prior to the eruption in July. So they knew this was all coming. They published a paper saying it was coming. paper didn't actually get published and issued back in 75 until after the eruption, but it was actually submitted for review before that. That was the era of the 70s, of course. So, but it was enough that the scientists could actually publish about it ahead of time. Yes, Dean?
They kind of need those preprint servers for that we see nowadays. You
Yeah,
can go and view the preprints as they're submitted, so you don't got to wait for that whole review process. It's, going through the weeds a lot more, but you get access to the information a lot quicker.
yeah, certainly the process would be, even today we see it sped up quite a bit, and of course there was no internet back then, of course, and that was the main issue. So that's the Volcano Watch series here, and then one last thing I wanted to point out here is interesting. This is back from an article we've talked about before. Volcanic Unrest from Mauna Loa. This is by Thalen Miklius and Christina Neal in 2017. And I will just come down here to point out that I'm going to read this sentence right here, which is where I get this term of burst here. 1 to 2 years prior to the 1975 and 1984 eruptions, swarms of small earthquakes increased in intensity. The strongest swarms included hundreds of small earthquakes per day for weeks. Bursts, as they were called, were separated by 3 to 6 months of relative quiet. So you have to wonder, 3 to 6 months of relative quiet in between bursts may be a way to describe what we've been seeing in activity this week. And is this still precursor to something to come? Or is this ongoing flank movement? That's really the question that we don't know. Is this ongoing flank movement allowing the flank is it moving out of the way fast enough to allow the volcano to inject without erupting, or is it a precursor to a bigger earthquake to come because we just can't catch up? And that's the thing to be determined, that we're still waiting to see. And the dead giveaway, of course, will be if we have something like a magnitude 5 or 6 on that southeast flank, whether it's Kauiki or Kilea areas, or even on Kona side, as proposed by recent researchers who think that's the area prime to go. So we'll have to wait and see for that. So that's a little bit of everything for 75. That's the context of it right there. And with that, we can turn to our final set of thank yous and questions, Dane.
All right.
We did have a $9.99 super chat from L. Lauer. Says, thanks for your hard work, guys. Great content. Really appreciate you. Appreciate that donation.
Mahalo.
And I do want to shout out, we have some donations on the HawaiiTracker.com site /support that came through. Catrin G, Jana K, Judy P, Lori H, Robin M, Victoria D, Linda H, and Dave P. Really appreciate it, guys. So there's not a lot of questions here. There's actually not any. So I sent you a link on the Kine, and it's a paper or report that got put out not too long ago that was looking at the 2.5 PM, the fine particulate matter that we see around the world from their sensor network. That their report was put out by IQ Air, and it's just kind of air quality. And the interesting about it was how many locations on the Big Island of Hawaii got put into the least polluted regional cities. And this is for North America. We kind of get lumped in with the US and Canada. I guess I didn't know where else to put us. But yeah, we had 7 of the top 10 spots
For the cleanest air in the country in North America are in Hawaii. We're talking about cities with population over 5,000. The thing that they were saying in the research is the primary factor that is polluting the air is forest fires, wildfires. And they say that up to 70% of the particulate matter can be attributed to that. And that's why a lot of these areas that are really poor. I see one of the towns I grew up in on the list for 2020 of the worst air in the country, right? So it's quite a difference on that. But the interesting thing is a lot of these towns on the Big Island also made the cut in 2019 for the lowest particulate matter that was being captured by these sensors. In 2018, nobody made the list on the island, and it wasn't a secret as to why, right? But it's just interesting that, we've had 35 years of the Pu'uo eruption capped with the 2018 eruption, which, bad air quality for the entire west side of the island for decades. and then like a light switch, once Kilauea turned off and the SO2 and the particulate matter went down to very small levels, the island cleaned up really quickly. The air quality did, at least. So I just thought that was interesting, something to share, cap it off with.
Yeah, for sure. And yeah, I've been showing you guys this Dane's post from July 6th on HawaiiTracker.com. Another good reason to go on a website there. You can read the whole article there and look at the details and all that here. That's Dane has just summarized here. And the link for you guys to see for yourselves is on there as well.
Right.
Mahalo,
and
Dane.
we are going to be premiering another episode of Drones On immediately following this stream. It will be covering May 29th and May 30th of the 2018 eruption. It's really some of the craziest days in the eruption right here. So much going on, so many things that are probably forgotten by many people, but we kind of want to preserve them. So that's going to be premiering right after this live stream. So stick around, check them out. It's not that long. I think it's only like 9 minutes. So yeah, hope to see you guys there.
Yeah, I'm definitely going to check it out, and I'm sure you guys are eager to see the next episode there. So mahalo, Dane, for continuing to share that. We'll look forward to the next episode in this long series. It was a long eruption, so it's got to be a long series, of course, too. Otherwise, we will see you guys once again in another week and talk about our 2 volcanoes and associated events on them at that point in time. So mahalo, everybody. Mahalo for your support. Mahalo for your questions and discussion here. Mahalo to the USGS HVO for all their data, and to all of our supporters, including Hawaii Community Foundation, County of Hawaii, and HawaiiTracker.com. All right, guys. He is Dane DuPont. I'm Philip Ong. Aloha, everyone.